Hello everyone. In this presentation, we are going to have a review on concrete ingredients, admixtures and IS method of mix design. We know concrete consists of cement or cementitious material, fine aggregate, coarse aggregate, water, and fifth, only when required, admixtures. The performance of the final concrete, its strength, durability, how easily it can be placed on site depends entirely on the proportioning. The quality and importantly, the compatibility of all these constituents working together. Get one of these wrong and the whole system suffers. Let us look at each ingredient individually, starting with cement. Cement is the binding material in concrete. It is the glue, essentially holds everything together. When you add water to cement, a chemical reaction called hydration takes place, and this is what allows the cement paste to develop strength over time. Now, there isn't just one type of cement. There are three types of cement we commonly come across: OPC, ordinary Portland cement, PPC, Portland pozzolana cement, and PSC, Portland slag cement. Each has slightly different characteristics suited to different applications. When we evaluate cement quality, there are a few properties we always check: fineness, consistency, setting time, and soundness. Fineness affects how rapidly the cement reacts with water. Finer cement reacts faster. Soundness is about preventing unwanted volume changes after the concrete has set. We don't want our concrete expanding or cracking later due to unsound cement. Setting time needs to be controlled so that we will have enough workability time to place and finish the concrete before it starts hardening. And of course, we need adequate compressive strength along with a stable, consistent chemical composition batch to batch. The bottom line here is cement selection isn't arbitrary. It has to suit the required strength, durability, and the specific exposure conditions the structure will face, whether that's a marine environment, a sulfate rich soil, or ordinary atmospheric conditions. Moving on to fine aggregate, this is usually natural river sand or increasingly today manufactured sand, often called M sand. Fine aggregate fills the voids between the coarse aggregate particles and plays a major role in improving the workability of the fresh concrete. The grading of the sand means the distribution of particle sizes has a direct effect on water demand, on how easily the concrete can be finished, and on the risk of segregation where the coarser and finer particles starts separating out. Practically speaking, when we are checking a sample of fine aggregate, we can look at its cleanliness, its grading curve, the presence of any deleterious or harmful materials, and its specific gravity. Fine aggregate must consist of hard, strong, clean grains, generally smaller than 4.75 mm, and it needs to be chemically inert. Any organic impurities, clay coatings, or excessive silt content can seriously compromise both the setting behavior and the long-term durability of the concrete. Naturally, all of this needs to conform to the relevant Indian standard specifications. Coarse aggregate. This is the material retained on a 4.75 mm sieve, and it forms the load-carrying skeleton of the concrete. It provides the bulk volume. Common nominal sizes we will encounter are 10 mm, 20 mm, and 40 mm aggregate, chosen depending on the application. Thinner sections need smaller aggregate. Mass concrete can use larger sizes. The shape, surface texture, the grading, and the inherent strength of the aggregate particles influences the performance of the concrete. A well-graded aggregate, meaning a good mix of different particle sizes, reduces the void content, which in turn reduces how much cement paste we need to fill those voids. It is efficient and it is economical. One thing to watch out for: flaky and elongated particles. These irregular shapes tend to reduce workability and can create weak planes in the concrete. So their proportion needs to be controlled. And just like fine aggregate, coarse aggregate must be chemically inert, strong, clean, and properly graded to ensure the concrete achieve its intended strength and durability. Next, water. It seems like the simplest ingredient, but it is arguably one of the most critical ingredient in concrete. Water is required for two things: hydrating the cement and providing workability so the fresh concrete can be mixed, placed, and compacted. Though excess water is dangerous, here is the catch. Any water beyond what is needed for hydration ends up creating capillary pores within the hardened concrete once it evaporates. And this directly reduces both strength and durability. This relationship is captured in what we call the water cement ratio. And I want you to remember this term because it comes up again and again. It's one of the single most important factors governing the strength and durability of concrete. Water quality also matters. As a simple rule of thumb, if the water is safe enough to drink, it is generally suitable for making concrete. It should be free of oils, salts, sugar, and organic matter. And a word of caution for site practice: avoid the uncontrolled ad hoc condition of water at the site just to make the mix easier to work with. That is one of the most common and most damaging practices that compromises concrete quality in the field. Let us shift to admixtures. Admixtures are materials that we add to the concrete either before or during mixing, specifically to modify its properties in some controlled way. Why would we use admixtures? To improve workability, to control setting time, to enhance strength development, or to improve durability. In many modern mixers, admixtures are used to reduce water demand while still achieving good pumpability and ease of placing, which, as we just discussed, is a huge win for durability since we are not adding excess water. But the dosage and compatibility of any admixture must always be established through trials. We should not add an admixture based on a textbook number and a hope for the best. And admixtures are not a suitable substitute for good mix design. They do not replace proper proportioning and quality control. They enhance a mix that is already fundamentally well designed. Chemical admixtures and its major categories. First, water reducing admixtures, also called plasticizers. These reduce the water demand for a given workability. Then we have a high range of water reducers or superplasticizers, which allow us to achieve high workability at a low water content. These are extremely common in modern concrete practice. Next, accelerators, which speed up the setting time or the early strength gain, useful when you need rapid formwork removal or you are working in cold weather. On the opposite end, retarders delay the setting time, which is particularly useful in hot weather conditions or when concrete needs to be transported over long distances before placing. And finally, air entraining admixtures, which introduce controlled microscopic air voids into the concrete. These are especially important for improving resistance to freeze-thaw cycles. All of these chemical admixtures need to meet specific physical and chemical characteristics to reliably deliver these effects, and they are typically required to comply with recognized standards such as ASTM C494 or EN 934-2. Mineral admixtures or supplementary cementitious materials. Beyond chemical admixtures, we also have mineral admixtures called supplementary cementitious materials or SCMs. Fly ash is one of the most widely used mineral admixture in concrete. It improves the workability in the fresh state and enhances durability at later ages. Ground granulated blast furnace slag or GGBS contributes to durability and importantly reduces the heat of hydration, which is valuable in moss concrete pours where thermal cracking is a concern. Silica fume produces very dense, high strength concrete often used in high performance applications. And materials like metakaolin and other pozzolanic materials are used for more specific and specialized applications. For all of these mineral admixtures to work effectively, they need particular characteristics: high reactive amorphous silica content, extreme fineness, and low carbon content, so that they can react with the calcium hydroxide produced during cement hydration, fill in microscopic voids, and contribute to long term strength gain. The selection of which SCM to use really depends on the required performance, local availability, and applicable standards. Next is admixture selection precautions. Before we move on to the mix design, a quick but important checklist of precautions when we using admixtures. Always follow the manufacturer's recommended dosage range. Don't guess. Check compatibility between the admixture, cement, and any supplementary cementitious materials we are using together, since incompatible combinations can cause serious problems. Avoid overdosing. This can lead to excessive retardation, segregation, or other defects that are hard to fix once the concrete is placed. Always carry out laboratory or site trials before going for full production. And finally, we have to keep good records: the dosage used, batching conditions, and the observed performance. So we can build a reliable knowledge base over